And now we come to the triangle inequality, which is a very basic but super useful inequality in linear algebra, in analysis, that is advanced calculus, and in functional analysis, and all kinds of places. So if we've got two elements of an inner product space, then the size of their sum is less than or equal to the sum of their sizes. Okay, and so I guess I should point out here that if you have that this proof is for the case when we're in an inner product space. So namely, when the magnitude or when the norm is defined as the square root of an inner product of an element with itself. If you're just working with a general norm and it's not given in terms of an inner product, then this is not a property that you prove, it's a property that you assume, because the triangle inequality is part of the definition. So what I'm proving right here, I guess, is one part of the idea that if you have an inner product, then this formula right here actually defines a norm for you. And one part of that is proving that, well, you have to prove that all parts of the definition of norm are satisfied. And so for this one here, I'm checking the triangle inequality part. So let's see. So if we do magnitude u plus v squared, then once again, doing what we do, this is going to be u plus v in the inner product, which, as we saw before, is magnitude u squared plus 2 real part of inner product uv plus magnitude v squared. Okay, so that's as we've computed a couple times before now. And so the idea is that we can introduce an inequality right here by noting that the real part is less than or equal to the absolute value. And so at this step right here, basically I'm appealing to the inner product holding for the absolute value in the complex plane. So if we go to the complex plane and we have some vector, then the absolute value is going to be this right here. So this would be the absolute value of z. I guess I should have labeled my stupid z first. There's my z. And then the real part is going to be this part right here. So that's the real part of z. And so by the triangle inequality, just in good old C, which everybody knows, then we get this inequality between the real part and the absolute value. So now we can use Cauchy-Schwarz to say that this part here is less than or equal to the product of the magnitudes. And then this thing is the foiled out version of the sum of the magnitudes squared. And so now you just need to take square roots of both sides and you get the triangle inequality. The end. All right. So once again, it's interesting to notice, like, okay, when do these things coincide? So note that equality holds in the triangle inequality here if and only if the real part of the inner product uv is equal to the magnitude of the inner product, or the absolute value of the inner product, which is equal to that product by Cauchy-Schwarz. And so now, what does this tell us? Well, this tells us a couple things. So first off, based on the fact that we have this expression right here, we can see that from this part being equal to this part here, it must be the case that UV is, or the real part of UV, I should say, shoot, where's my thingy, there we go, is non-negative, because this one right here is a non-negative term, right? And then what else can we say? So we know that if these guys are going to be equal, going back to our picture over here, you can see that that happens if and only if what did I even draw that for? If and only if the inner product is real. All right, so putting these two together, we have equality if and only if UV is a non-negative real number. All right, so now combining that with the fact that the Cauchy-Schwarz inequality here holds with equality, if and only if one of these vectors is a scalar multiple of the other, then here we know that lambda has to be non-negative. All right, so tying that all together, we have that u plus v in absolute value is going to be equal to magnitude u plus magnitude v, if and only if u is equal to a positive scalar multiple of v. So in other words, they're both parallel and they both lie on the same side of the origin.